So I think I can try. You want me to share my slides now?
Yeah,
Let's
we can
see.
actually check. We can verify if it is working. Yeah, we can see the slides.
Okay. Okay, maybe I can put it. I made myself a big coffee.
For 2011. Yeah, so you were also there, right? Oh, okay. Okay, so I think we can start now. So okay, so we are happy to have Professor Ivette Fuentes as the 26th speaker in the series of IYQ colloquiums, which are being organized at TCJ Crest, Kolkata, to celebrate the International Year of Quantum Science and Technology. Professor Fuentes is at University of Southampton, UK. She is also a fellow at Keble College, Oxford. She obtained her PhD from Imperial College, London. She has held positions at University of Oxford, Perimeter Institute, Canada, University of Vienna, Austria, UNAM, Mexico, and many others. She has won many accolades for her work. Professor Fuentes' main area of interest is interface of quantum theory and general relativity. So, Professor Fuentes is speaking very early. I mean, she is in Mexico. So, I think it is about 6 a.m. there. So, we thank her for taking time to speak to us. Now, I request Professor Fuentes to deliver her talk on should we quantize gravity or gravitize quantum?
Thank you very much. Thanks everybody for being here at this talk, and especially to all the organizers. I'm truly honored to be considered as a speaker on this amazing list of speakers celebrating this quantum year. So it's a great honor for me. And we were just talking that I visited India. I think it was like almost 20, no, well, maybe 15 years ago, a long time. So it's nice at least to be remotely there, hopefully, maybe in person one day, not in the far future. So I want to talk about this question that Roger Penrose likes to pose. Should we quantize gravity or gravitize quantum theory? So I want to tell you more about this question. What does Roger mean? And how I have been trying to address this question with my research and my group at the University of Southampton and Oxford. So I've guess the whole interest in this question is also motivated for many very interesting questions in fundamental physics that are unanswered. So I made a list here of some of the ones that I am interested, but of course there's many more. So, for example, what is the nature of dark matter? Is dark energy the driving is driving the accelerated expansion of the universe? What's the physics of the universe at early times? And also very relevant to the talk today, does the equivalence principle holds to quantum systems? So I will tell you about a recent experiment by Ron Follman where he addresses directly this question, and there seems to be already some experimental answer to this question. So, underpinning our difficulty to find answers to all these very interesting questions is sort of once I heard someone say the big elephant in the room is that quantum mechanics and general relativity are incompatible. So, we have theories that are applicable at different scales, but they're like all like pieces in the puzzle that doesn't really fit in together yet. So, well, when I learned quantum mechanics and general relativity at university, my teachers would explain to me that quantum mechanics applied to very small scales where electrons, atoms live to very few particles. Perhaps when you had many particles, then you would start transitioning into the classical world and to small speeds and so on. And that then general relativity applied at the large scale. So starting from the scales of, let's say, Earth, if you consider satellites already make corrections due to general relativity and onwards. And of course, we know that GR doesn't explain dark matter or what people also call dark energy. But let's say roughly this is how we see modern physics. But I'm going to show you that experiments already show us that this sort of division into small scales and large scales is no longer true. And this is also very relevant for us understanding the interplay between quantum physics and general relativity. So I like to focus in this talk in the simple case of quantum physics, which is spatial superpositions. So if you think about even having a small system like an atom in a double well potential, in quantum physics, the state of the system allows us to describe a superposition state in which the atom might be in the same with the same probability on the left and on the right. I mean, sorry, I'm 6 in the morning. I have my coffee here in case my brain doesn't work so well. So in a superposition of left and right, no, and this is sort of a simple situation, yet very complicated. We haven't for 100 years been able to exactly say what is a quantum state, a superposition state like this. Is it really that physically the atom is in the left and the right at the same time? So if you took that route, some scientists do, then you would be immediately confronted with the question about, well, what is mass in that case? Because if you can have the system, you can have it in many places at the same time. So how do we understand mass in that situation? Do you have n times the mass? Of course. Well, I would say, of course not. That doesn't make sense. But even the whole notion of particle becomes complicated. And well, this very recently there was this poll that perhaps many of you participated in which we were asked, what did we think about the what is the explanation of quantum theory? What are the, let's say, the state, which is the basic thing in quantum mechanics? How do we understand it? And you know that there are many different interpretations. So the Copenhagen interpretation would say, just shut up and calculate. This is how quantum mechanics is, and we just don't need to even maybe try to understand deeper what is this superposition, what does it mean? But we just need to understand, like, accept that nature is like that at small scales and work with it. But as we will see, it's not really that clear that quantum mechanics applies only at small scales. And there are many experiments, and I'm going to show you one in which this becomes really relevant actually to understand exactly what we're talking about. But there are many, and interesting enough is that as we have progressed in our manipulation of quantum systems, and we've made progress in quantum optics and in many uh, directions, including quantum sciences. Uh, as more as we make progress in that direction, we have more and more and more interpretations popping out, which maybe means that we really haven't made much progress in understanding what are essentially quantum mechanics. So, for example, you also familiar with many worlds or collapse models and so on. And what you see from this poll is that there is no consensus. Still, there's more people following the Copenhagen interpretation, but with very little confidence. And well, I voted a new, which is what I'm working on with a bit more confidence, hopefully, because I've been working on it from my own understanding. But this is the state of things at the moment. So I followed the Copenhagen interpretation for a long time as a student because I was interested in these questions, but felt very incapable of addressing them. And I just took the route, okay, let's shut up and calculate. But more recently, I've become really uncomfortable with these things, and not only uncomfortable, I would say more like interested and curious. In particular, I would like to understand in a deeper sense what is mass and what is time. And of course, this a question about spatial superpositions is very important in this case. I worked at the interface of quantum mechanics and general relativity for a long time, but I was taking a different perspective. I was using quantum field theory in curved space-time, and I was asking questions about entanglement in relativistic settings using this formalism. I was interested to understand, for example, entanglement in black holes, or what happens with entanglement in cosmological settings like an expanding universe and so on. And one of the most interesting things that I learned of quantum field theory in curved space-time is particles are ill-defined. And when you have a curved space, the notion of particle breaks down because the vacuum between inertial observers is not equivalent. So different inertial observers see different particle contents in the field. So when I started to try to study entanglement in these systems, and coming from a quantum optics background in which we first define our bipartition and then we can talk about entanglement, I the first problem I had was that couldn't even define what the bipartition was in curved space because of this inherent problem that the notion of particle is indefined. So in quantum field theory, in curved space-time, fields are fundamental, not particles. And this also is an interesting question when one thinks about trying to understand mass at a fundamental level. So I have here a little, let's say, summary. Of course, this is not comprehensive, but on how could we view some of the, let's say, inconsistencies between these two theories. So in quantum theory, time is absolute. And this is because the transformations underpinning Quantum theory are Galilean transformations, as in classical physics. So all clocks tick at the same rate, and space and time are very different notions as they are in classical physics and in our own experience. And we can see, for example, in the Schrödinger equation, that space and time are treated very different. Time is a parameter, positions can be quantized. The Schrödinger equation has a first order derivative in time, but a second order derivative in space. So they're treated very different. And then we have situations like the one we were just talking about just now, that we can have a particle in a superposition of two different locations at once. And now, if we jump into relativity, space and time actually belong together in the notion of space time. So they're not really different. They sort of become, in a way, one entity when you bring them together. And in Lorentz transformations, space and time mix for different observers. So time and length are observer dependent, no longer absolute. So they depend on the state of motion of the observer. And then we get that if we have a mass distribution, therefore a curvature of space-time, and we look at two different points in space-time, let's say two different points in space, we would see that time flows at different rates. So how could we understand the situation of having a spatial superposition where time flows at different rates in the superposition? Well, this is a simple
Yes, I do.
situation. Yes. Oh, I heard something. Is there
T A
a
N Y.
question? Excuse me?
No, so sorry, please continue.
Oh, okay. Yes. So how can we understand this situation of having a superposition with time ticking at different rates at different points in space is something that our current theories could not address yet. So now, if we come to considering a massive system in a spatial superposition, well, this is an interesting situation to understand this interplay between quantum theory and gravity. If you think you have your system, and because it has mass, it curves space-time. So if you now consider the system in a superposition of two different locations, in a way, you have something that looks like a superposition of two space-time configurations. So how could we understand a situation like this? Actually, we have a situation like this all the time. I mean, we put quantum systems in superpositions, and uh, I'm going to talk about how massive the systems are, but Marcus Arndt can put molecules in a superposition. Of course, they have mass and they have their gravitational effects, but they're usually very small, and they do not sort of, they can be neglected. But as the system becomes more massive, and I want to talk about the scales where these become relevant, then we want to understand if this situation is stable or not. There are reasons to believe that, the things are different for gravity, because gravity is the only force that has a equivalence principle. Of course, in DR is not seen as a force, but other forces do not have an equivalence principle. So in that sense, it's different. So it might be that the way to quantize it is not the same. So these are very interesting questions. And here's where Roger poses this question: should we quantize gravity or gravitize quantum theory? And what he means by that is, since the principles are enough, it's important to determine which principles are really fundamental. So the program of quantizing gravity is seen as, let's say, keeping the principles of quantum theory as fundamental, and then trying to modify general relativity in order to be able to unify the theories. But Roger prefers the idea of gravitizing quantum physics. So this would mean keeping the principles of general relativity as fundamental and modifying quantum theory. And the reason why he thinks this is the way we should proceed is because quantum physics has a problem, for example, that I mentioned before, that we don't know what is the ontology of the wave function. And we also have the measurement problem. So since quantum mechanics already has these issues, he thinks that it has to be modified anyways. So I think that they should be both modified in order to unify them. And I think Roger would agree with that too. And I've been working in this direction in the last years. And well, I also wanted to mention work by Jonathan Oppenheim, who has proposed that the way to unify quantum theory and gravity is considering gravity to be classical, somehow with some stochastic properties, and arguing that, as I said before, gravity is different and therefore might, in his view, not should not be quantized. In my view, it should be quantized. But well, the difficulties to find how, in my opinion, are really, let's say, the struggle has a lot to do with us not having instruments and experiments to guide our theories. So I found this image in the internet and I liked it very much because I thought about humans looking at the sky and looking at the stars with our own eyes, and from there trying to make sense of who are we, what are we doing here, what is this place, what is and so on, and how difficult it is by just looking at these little points in the sky to make sense of cosmology and so on. But then Galileo took the telescope and pointed out to the stars, and he was the first one who used this instrument to well, the first one we know, and to try to make sense of what's called cosmology and so on. And well, since then, telescopes have developed very much, and we have in many different frequencies and so on. And we can see now very far into the past of the universe. We can see that the universe is expanding. We can study things in detail, and then we can start making much better, more detailed theories in cosmology. And the same thing has happened in atomic physics. The Greek came up with the notion of the atom, and it took, I know, 2,000 years for us or something like that to be able to build instruments to look into the microscopic world and start making more serious atomic physics. So I really want to make the point that in order to progress in our understanding and making more significant theories, we really need these instruments. And when we come to scales where quantum mechanics and general relativity interplay, and I want to tell you more about the scales, we don't have instruments. So it's even worse than looking at the sky with our own eyes, because we don't even have our own eyes to look into the scales. We're really completely blind. We were, because that's one of the things I want to tell you today about how quantum technologies have made so much progress that some of them have already reached scales where relativity kicks in. And this makes us now really try to, let's say, step up with our theories so that we can actually explain these experiments properly. Oh, I would be very grateful if you could let me know maybe 10 minutes before I need to stop, because sometimes I lose track of time, if
Sure,
that's
sure.
okay. Thank
Sure.
you. So, well, this is what I've been trying to do with my group for many years, is that I've been trying to use quantum technologies and, let's say, cutting edge experiments to think about how could we push them, or how could we use them to try to put the pieces of the puzzle together and understand the unification of quantum theory and general relativity, but guided from the experiments themselves. So I would like that there are the experiments themselves that tell us what principles are fundamental. So there, as you know, many different directions in which we could use quantum technologies, and I want to focus in particular in three that I will discuss in a moment. But I guess what I would like seeing, and I think we have everything we need in order to do this, is to see this sort of a cycle happening in the study of this. Scales in which we have some pieces of the puzzle. No, we have some theories, some mathematics. For example, I don't know, one could think about quantum field theory in curved spacetime. This is already a theory that allows you to study effects at the interface of quantum mechanics and general relativity, but of course, is not the full picture. But we could start from something like that and then propose experiments, make measurements, and from there, let's see what things need to be explained so that we can get into the process of maybe asking things philosophically, thinking things deeper again, to try to come up with new ways of modifying our theories and then enter this cycle which we have actually in quantum technologies. This is what we do in quantum optics and so on. And that's why I think this has made so much progress. It would be nice to be able to do this as well when it comes to the unification of quantum theory and general relativity. And actually, I believe that one needs to, let's say, understand how quantum mechanics and general relativity interplay in order to be able to address the fundamental questions of quantum theory themselves. I don't believe that we can. Some of my of our colleagues believe, okay, first we address the questions of quantum theory. So I don't know, we look at collapse models and things like that, or your favorite interpretation of quantum theory, and then we can think about unifying for gravity. I think that we need to understand things together. So the quantum technologies that are relevant to these questions, I mean, I'm sure there are different ways of seeing this, but as I like to present it, is thinking about long-range quantum experiments where satellites operate, large mass, and also high sensitivity. And I want to show you how from these experiments we can see that this sort of idea that quantum mechanics applies only to small scales. You can already see that it's not the case with long range. And general relativity to large scales is known. This is clearly from the experiments we found out this is no longer true. So when I started to study quantum optics, uh, that was my background. These were how experiments look like. They were tabletop experiments in which people would use photons and they would sort of demonstrate entanglement and teleportation protocols in tabletop experiments. And now, well, there's been a Nobel Prize for these beautiful experiments demonstrating entanglement. But since then, these experiments have made huge progress and very driven by Anton Seilinger and with a former member of his group, John Wei Pan. They have been even using a special purpose satellite for studying quantum um, technologies, quantum protocols using satellites and distributing entanglements through thousands of kilometers. So this is one way in which I meant this, that when I learned quantum theory, I was told quantum theory applies only to small scales. And yes, of course, here we're talking about photons that are massless, but we can see that we can hold entangled states across thousands of kilometers. Of course, it becomes very interesting to see if one can go beyond in this direction. I don't see why not. I don't see any fundamental problem with this. So this is very, very impressive, but very relevant for our understanding the unification of the two theories. And then at these scales, well, as I said, you have the interplay of quantum mechanics and general relativity. So it becomes very important to understand how the curvature of the space-time of the Earth and how relativistic effects affect quantum technologies like quantum teleportation and quantum cryptography. So I have a whole series of papers in this direction that I'm not going to talk about today, but we have looked how the propagation of wave packets on Earth are modified due to the underlying curvature of space-time using quantum field theory curved space-time. And we have said, what we have pointed out how quantum communications, quantum cryptography are modified by that. And we have also turned things around and used these changes in the wave packets. And it's not just gravitational redshift, which is a special relativistic effect that is already known and taken into account. I'm talking here about the real curvature effects. And we have then used these effects also using quantum metrology to say, well, we could use quantum metrology in order to estimate space-time parameters in this way. So this is a direction that I've been working on for many years. But I want to jump into a large mass, which is mostly at the core of what I want to talk in this talk. Excuse me. So um, how big can we put quantum systems in a spatial superposition? Well, the record is held by Markus Arndt at the University of Vienna, and he can put 2,000 atoms, like there are molecules that have 2,000 atoms, and he could put a molecule in a superposition. And well, I heard that he can do one order of magnitude more, but I'm not sure if this has been published yet. Marcus Aspenmeyer, also at the University of Vienna, can cool down nanoparticles made out of silicia. They have much bigger masses, like 10 to the 18 atomic masses, into the close to the ground state of a harmonic oscillator, so at quantum scales. But he hasn't been able to put it in a superposition yet, but he's working towards this. And there is a lot of work in the community trying to make these massive superpositions using different solids like diamonds, mirrors, cantilevers, rods, membranes. There's also work at Southampton led by Henrik Ulbrich, in which he has been able to measure gravity with these nanoparticles. It's not quantum yet, but I think technologies are getting there. But I also want to tell you about there, what it means, how far actually experiments are. So massive superpositions are very important also to understand the transition between the quantum world and the classical world. And Lajos Diosi and Roger Penrose independently started to argue that it must be gravity that let's say, affects quantum superpositions, collapsing them, and in that sense, explaining the transition between the quantum world and the classical world. So we don't see superpositions in our everyday lives. So one reason why we don't could be explained by the fact that when systems become massive enough, the superpositions collapse. And I like this idea. I think it makes a lot of sense from my point of view. So let's talk more about spatial superpositions and the equivalence principle, and try to find out if these are compatible or not, and under what circumstances could there be or not. So, well, in general relativity, at the core of the theory, there is the equivalence principle. So the equivalence principle tells us that if we are in a spaceship and we're looking at a physical system, we cannot distinguish if our spaceship is moving with uniform acceleration, let's say g, or if the rocket or a spaceship is in a presence of a gravitational field with the same g. But in this case, a uniform gravitational field. So we cannot distinguish between being accelerated or being in the presence of a gravitational field. And one of the consequences of this is that if we look at a small region around our system, we can get in a free-falling frame, and we can transform away gravity. And this is something that you cannot do in the other forces. So this is quite special. So let's start by making a distinction between passive gravity and active gravity. So uh, let's consider the Earth, and then the Earth and a quantum system in a superposition in the gravitational field of the Earth. So the Earth would have the active mass, in which the passive mass of the quantum system falls in the presence of the Earth. So the Earth, in this case, is the active mass, and the atom has the passive mass. In the same sense as when we look at the Earth moving around the sun, we would say that the sun has the active mass, and the uh, Earth has the passive mass moving around the sun. So this is to be distinguished from active gravity, in which we do not have the external gravitational field of the Earth, but we only have the quantum system. So if the quantum system is in superposition, then the active mass of the quantum superposition has a self-gravity effect. So in one case, it's external, and the other case is self-gravity. There's no external field as in the Earth. And this is very important, because when we look at the equivalence principle in these two cases, the results are very, very different. So let's first think about passive gravity. So just for the time being, think about being in the gravitational field of the Earth. So we're in a lab, and we're describing an atom that is falling in the lab. So, and we describe this atom, we describe the quantum state of this atom. And Roger argues here that we can look at two different frames. So one would be the Newtonian frame, so this is the lab frame, in which we describe the system. And then Roger likes to think about how would we describe this state if we then got into the free-falling frame with the atom, which he calls the Einsteinian frame. And this is something that in quantum theory we don't do. We don't change frames. I mean, we could, but we usually don't, because time is absolute. And let's say if you looked at a vacuum state in this case, there all the vacuums are equivalent when you look at different inertial observers and so on. So let's say it's not very interesting to do so. But in general relativity, sort of that's what we do all the time, is that we want to explain the physics from the perspective of different observers. So Roger was interested in finding out how quantum superpositions and the equivalence principle can be looked at from the perspective of different observers in this sense. So he says, okay, if the state of the system is described by a quantum state in the Newtonian frame, the state has to be the same in the Einsteinian frame. However, you know that in quantum theory, states are equivalent up to a phase. So there could be a phase, and actually he calculated this phase using Newtonian gravity. And what he finds is a funny dependence on time. So the phase depends with the cube of the time. And so what he argues is that if we want quantum theory and general relativity under this passive gravity situation to be compatible, the states have to be the same up to this phase. And if we are able to measure this phase, then we could argue that the equivalence principle and the superposition principle are, let's say, compatible under passive gravity. So, well, you know that a global phase cannot be measured. And Ron Foldman did a beautiful experiment converting this global phase into a relative phase by making this sort of hybrid interferometer, in which he takes the atom and he prepares a spatial superposition of this atom, in which in one branch the atom is at rest in the lab. So he uses magnetic fields to make the atom levitate. And then in the other branch, he gives, with using also fields, a kick to the atom. And he then has a situation in which the atom that is kicked is in free fall. And then he lets the atoms interfere, and he looks at the interference pattern. And for this, he uses this chip in which he traps the systems, and he manipulates the currents through the chips to make this a very special situation, this hybrid interferometer. And well, the beautiful news is that he actually measured this T cube phase. So he invited me and Roger and other theoreticians as well to look at the experiment and to discuss among us, to interpret the results. And well, as Roger and I see it, this is a very important experiment because although this was theoretically predicted many years ago, it was not confirmed by the experiment. This type of interferometer was not realized before, and it is very clear that the phase dependence goes with the time cubed. So this is for us very, very good news, meaning that maybe how Roger looked at this problem was correct. But now the interesting thing really happens when one goes into active gravity, because DLC and Roger predicts that in this case, the superposition principle and the equivalence principle are not compatible, they're in conflict. And the reason why is because if you look at active gravity, so you look at the self-gravitational field of a massive system itself, in this case, you cannot play this game of looking at the quantum state from different um, reference frames and getting into, let's say, a frame in which you can cancel out gravity. You cannot cancel out gravity. So there, Roger looked at this as an energy uncertainty of gravitational origin that we know as the gravitational self-energy of the difference in the superposition. And he came up with this formula here, where this is the mass density of your quantum system in the left and in and the right, and you can see here the Newtonian potential. And Diossi came up with the same formula 2 years before, but completely independent, not using arguments, relativistic, purely classical arguments, thinking about, well, if you have a system and then a copy of itself, and you then try to separate let's say, look at the superposition, then there would be this active gravity. Then Roger uses an uncertainty principle to argue that then there is a time scale in which we would therefore expect the system to collapse because of this incompatibility between the equivalence principle and the superpositions. This would mean that superpositions are unstable and they would collapse, explaining why we don't see quantum superpositions in our daily lives. Now, there is here a caveat to consider, is that this energy uncertainty principle, as written here initially, actually only holds under unitary evolution. So if you're thinking that the system collapses or reduces in some sense, you cannot strictly use this equivalence principle, sorry, uncertainty principle. So one needs to be very careful with this, and this is something that I am working with my group at kind of refining this. But as you can see, it is that a first step, let's say, that to try to extract a time scale from the idea of active gravity and the self-gravitational effect of the system. But this has to be taken with care, and that's one of the things that we're doing at the moment in my group. But when I met Roger at a conference and we started to discuss different aspects of quantum theory and relativity, because I always been interested in these questions, he was telling me about how he thought collapse was a key ingredient on understanding the unification of the theories. And he explained to me that people had not been able to test this in the lab because people had not been able to cool systems to the, let's say, quantum scales. All the experiments taking place at the time were using solids, and solids are very difficult to cool down to very cold temperatures. And at the moment, I was working with Bose-Einstein condensates that can be cooled down to half a nanokelvin. And I thought, well, maybe we could look into that and what would be the, let's say, the pluses and the minuses of looking into that. So a BEC, you have atoms, which are bosons that you can cool down to the ground state. And of course, you cannot reach zero temperature. So you can't really cool all your atoms to the ground state. They have interatomic interactions, they collide and so on. And these populate higher frequency states, which we know as phonons. But it's a system that is very interesting because you can have up to, I mean, the record is like 10 to the 10 atoms in hydrogen. In sodium, people have reached 10 to the 8, maybe close to 10 to the 9. And typical rubidium experiments have more like 10 to the 6 atoms. But I was curious to find out what would happen in this case. So I was very lucky to be able to work with Roger and publish with him exploring this situation. And the problem with the BC is that you have to prepare a null state. So all the atoms on the right in a superposition of all the atoms in the left in a double well position, and this is impossible. I mean, the moment that you lose one atom, the whole system collapses. But I was interested in finding out what you could do in this direction. And I found a good lesson because sometimes you look at things that look really impossible or are really impossible. But if you step in and still explore, then you might find interesting things and find a way to turn things around, which is what I'm doing now, and find, let's say, a alternative way to do things. And I want to tell you what I'm doing at the moment in this direction. So what we looked at with my postdoc at the time, Richard Howell, is that we looked at two body losses, three body losses. So the biggest reason why you lose atoms in the superposition is because of three body recombination. So we calculated for large particle numbers what are the rates of loss and so on, and other sources of noise typical of the system. And well, what we found, and this number actually applies to all the other cases of solids and also as well, that in order to reach the scales where the gravitational self energy of the difference would tell you that the time scale where things would collapse, you need around 4 times 10 to the 9 atoms to see the system collapse due to gravity, let's say at 2 seconds. So what you want to do is have an experiment in which you can keep the coherence for a very long time. Let's say 1 or 2 seconds. This is really far away, not, but realistic. I mean, it's not impossible, let's say, to push the time. So people usually do milliseconds. Um, and then you would have to have the system consisting of 4 times 10 to the 9 atoms. So if you compare to what the record is currently that I mentioned to you, that is by Marcus Arndt, something like 2 times 10 to the 3 or 2 times 10 to the 4, we're many orders of magnitude away. Um, so I'm going to tell you in a moment more about how I think we could address experimentally this question. But well, Diossi took a step. Roger just told you there is a time scale where the gravitational self-energy of the difference would tell you that the state collapses, but he didn't go beyond that. He just gave this formula. Diossi took a step forward and made a stochastic equation, so a microscopic model explaining the sudden collapse of the wave function. So this is known as the Diossi-Penrose model. And the model has some problems that actually Roger doesn't like, and I agree with him, which is energy is not conserved. So because energy is not conserved, there's a prediction of a spurious radiation. And there's been an experiment done a few years ago in which this radiation was not observed, ruling out many spontaneous collapse models, including the gravitational one, up to some so let's say scales. No, it's still possible that DOC's model holds at other scales, but to the scales and the masses explored in the lab, the radiation was not observed. So there was some news on in the newspapers saying that Angelo Bassi proved Roger Penrose wrong, and Roger was upset because he was saying, "Well, it's not even my model is DOC sort of gave this collapse stochastic equation, and Roger didn't like the fact that it was not energy conserving, and well, it was kind of ruled out up to some masses where we were expecting that maybe we would see something." So that's where I decided to start working seriously on this problem. I became very interested in finding out if we could now make a different model, um, uh, and trying to address, to start with, the question of the energy conservation. So I'm going to speed up because I think I'm running out of time. So this is what I've been doing in the last 3 years. I haven't been publishing much actually because I've been focusing on this problem, but I've been very lucky to be supported by a donation that has allowed me to have the time to really focus on this question that has really required this time. And well, we have some results we haven't published yet, in which we are now been able to develop a new model completely different to the Joseph Penrose model, which also gives you the collapse and the reduction of the state, but in an energy conserving matter, and it has other very beautiful features. This is a teaser so that you keep posted for hopefully the paper will come out soon, but I'm not sure. One needs to do things very properly. But in the paper, we're also proposing an experiment. So I was talking about how in a Bose-Einstein condensate, it is a problem that you lose atoms very quickly, so you cannot make a new state. The record of the new state is 2 atoms by Chris Westbrook. So really very far away from anything useful. But the fact that atoms are not bounded because the BEC is not a solid, it's a fluid, you have tunneling between the two different wells. And then, because you have tunneling, you have a whole family of more interesting states, like two-mode squeeze states, or some family close to two-mode squeeze states, which are a much richer type of quantum superpositions that you cannot have on a solid. So people were saying, well, why don't you use these states then maybe to explore gravitational effects? And the reason why is because there were no formulas for the gravitational self-energy of the difference that could help you study the scales. So this is something that I've done. I developed a new model with a new formalism, and that has allowed me now to study what are the gravitational effects for these sort of states. And that is the experiment that we're proposing in what's coming up. So this is my team. So my team ranges from Melanie, who was in an experiment in cold atoms, but now is doing numerical work, helping us simulate things for the experiment, to a mathematician like Kia, and Abdul, who's a philosopher, helping us interpret the meaning of and the results, the interpretation of the new model. And then Hector and Ethan are like me, physicists with a background in quantum and GR. And well, I am not going to talk about high sensitivity since I ran out of time. Maybe I just want to say that there's really urgency for us to understand this interplay, because when we look at quantum clocks are so precise that there are papers claiming that the proper time that they can see the difference in proper time, not between the Earth and a satellite, but within millimeters, sorry, not millimeters, centimeter scales. Maybe some papers claim even millimeter scales, which is really the size of the sample itself. So you would see a quantum clock where the atoms on the bottom of the sample see a proper time different from the top. But in order to make these atoms, these clocks more precise, people are working towards entangling the atoms. And in this case, you are really at a scale where you have quantum theory and general relativity interacting in a way that we don't understand. So in order to be able to explain these experiments that are already taking place, we're forced, our theoreticians, to come up with a better theories. But the wonderful thing, as I hope you got the message from my talk, is that now we can start doing this, being guided with the experiments that, in my opinion, this was the missing thing in our understanding. So this is, I always have so many other things in case I have time, and of course, I never have the time. So I just want to finish saying that, well, the wonderful news is that this donation is supporting a new Bose-Einstein experiment that Philippe Boyer and Chris Westbrook will be conducting at the University of Amsterdam. So the three of us are working together towards testing the aspects of this new model, which is inspired by DLC's and Penrose's idea of a collapse, but has some sort of different features. And well, we are hiring experimentalists with expertise in cold atoms to work in this experiment. And well, if you want to hear a bit more, there are some videos on YouTube that go into other aspects I wasn't able to cover today. And there is a new video that came out yesterday where Roger and I are in Kurt Jumangel's channel discussing these issues. So if you want to look at that, a little commercial in that direction. And I thank you very much for your attention. And if there's any questions, of course, I'm happy to answer.
There are questions, I think, online. I don't see any question. Actually, I mean, Professor Pandul also gave a talk in this series, and he did talk about the space factor.
You know what? The sound is very bad. I'm not hearing you.
Hello.
Okay.
Oh, yeah, hello. Can you hear now?
Yes, much better. Thank you.
Okay, okay. So, I mean, so you are trying to see this, I mean, this collapse of wave function by making the system larger, is it? Like having 10 to power
Yes.
9 atoms. So this whole idea of that collapse maybe due to gravity is for a very specific type of system. It is not this. It is not going to solve the conventional problem of collapse, right? When we make a measurement, system collapses to some other eigenvalue. So it has nothing to do with that. When we talk about gravity collapsing the wave function.
Um, no, we are trying to solve this fundamentally from first principles. Um, and then, I mean, the let's say the model that I am developing, the new model, starts from first principles, and it's applicable to any system that has mass. But then, in order to test it, that's when we go then specific. Okay, so in order to test the model, then we proposed testing the model with a double well, with a multi-particle interferometer, by looking at states that people can already prepare, instead of looking to these impossible to produce in the lab states like the known states. But that's like, the theory is a general theory, and then we can specialize it to a particular, let's say, incarnation of the theory.
Okay, but suppose particle masses are very small. We are talking, right?
Oh, I think you just need to keep the microphone close to you, because I sorry.
No, that's okay.
Thanks.
No, so but we can think of quantum systems which are very small, very low mass electrons, say for example, right, which can exist also in superposed state, right? So,
Yeah, so in
so what about collapse there?
yeah, so for very small systems like electrons, the effects are there, but
Mhm.
they're negligible. So I start like saying, fundamentally, you know, the the you need to consider gravity, and the states are there, the effects are there. However, they are negligible for one atom. For an electron, it's not that. Yes, of course they're negligible because the collapse time is so long that you would never see it. So for an atom, it's 10 to the 20 seconds. So it
Mhm.
doesn't mean it's not there, it's there, but you would not see that occur in our experiments. So if you want to see that in a in experiments, you need to have more mass.
Okay, so but it has no bearing on the conventional problem of wave function collapse, is it? Or
Um,
as it has any bearing on that?
no, but in the work that I'm doing, I will start by addressing that question. I would say by saying, well, we might have been looking at superpositions in the wrong way,
Okay, okay.
because we do it without gravity. So
Mhm.
this is a new proposal for how to look at things from a fundamental point of view, and then let's say take it from there.
Okay. I mean, there are some papers where people try to see the entanglement created by gravitational interaction, right? But
Yes, yeah,
uh,
that's a different approach.
okay,
Yeah, that's a different approach. But you know what I'm very excited about is that people come up with different approaches. I mean, mine is just one more approach, let's say. But the nice thing about them is that we can propose experiments.
yeah, that's what is.
The,
Mhm.
this is the thing. I mean, it's like everybody now, can, okay, come up with your own approach, come up with your model, and let's test them and see, because maybe it could be that we have to combine things. Maybe, well, one of the proposals comes close enough, but not quite, and we need to modify it, but we learn how to modify it by the experiment itself. So what I'm really excited is to enter an era in we can study the unification of quantum theory and general relativity guided by quantum technologies and experiments. I think that is the main point that I want to make. I mean, I, of course, have my particular way of doing it,
Right, right,
which might be right or wrong, you know.
right,
But I think the beautiful thing is that we can uh, go to the lab
right,
and
right.
test our models.
Mhm.
And of course, this is under the umbrella of gravity collapses the wave function, which is, uh, um, Diossi and Penrose sort of arguing in that direction that it should be gravity that helps us explain the transition between the quantum world and the classical world, or resolves the measurement problem, and so on. This is what I'm doing is under that umbrella.
Sure,
But I do it in a particular way.
sure, sure.
Hi, Professor Fuentes. I'm Shivdas. I have a question. You mentioned that the group that Marcus Arndt's group, right, created a
Yes,
superposition of 1,000 atoms, right? So what
yes,
mass scale
yes.
is that? Can you tell me?
Excuse me,
What,
could you say, I heard all your question except the last bit.
I mean, what is the mass scale of that? Like total mass of scale of that? Because I'm
Uh,
curious because I just want to know if it's actually less than or greater than Planck mass.
oh, it's much smaller
Okay,
because
okay.
look, the Planck mass, I think I'm going to say something very rough, okay?
Mm-hmm.
Is the scale that we were talking about with in our paper, that is like 10 to the 9 atoms, something like that. And in Marcus Arndt's experiment, he has 2,000 or 20,000, let's say, no,
Mm-hmm.
atoms in a molecule. So very roughly speaking, that's like, 20,000 atomic units. That's the mass. I don't know how to convert that at the moment in kilograms because I'm terrible at mental arithmetics. But we can convert it to that, but it's much smaller than the Planck mass.
Okay, okay. Mm.
You need to reach the Planck mass to see like the interesting effects, but very roughly speaking.
Okay, okay. Anything else? Wish to ask? Okay, so I mean, so actually, so once suppose you see this collapse of this wave function, then what conclusion one can draw from that? The,
So, well, I mean, what I'm trying to do is that that you see the collapse, but you see, how do you distinguish the collapse that is due to gravity or due to something else? Because it's noise, it's very difficult to say, what it is. But the new model that I'm working on has some features in which you would be able to, let's say, you would be able to read from your experimental data if this is of gravitational origin or not. So there is a signature, right? So let's
Right.
say that the experiment is successful and we're able to conclude, yes, gravity collapses the wave function.
Yeah, I think that
Well,
that will be great. I
so,
mean, if you can show that.
yeah, I mean that would mean we solve the if we measure that in the experiment, we solve the measurement problem. We are able to explain in a consistent way the transition between the classical world and the quantum world, and you also found a way of unifying quantum theory and gravity. So it's a big thing. Would be a big thing, you know?
Okay, sure.
But that, of course, the experiment, one can come up with a model, and that's already very nice. But at the end of the day, that's nothing if the experiment says that's not the way it goes. No? So it's really up to the experiment to see if our models are right or wrong. But the experiment is the guide. It's what tells us what works and what doesn't work. That's where I want to go.
So how much time scale we are, I mean, there for this experiment to be done, say a few years? I mean,
5, we're looking at 5 years.
oh, five.
Yes, because the states can be already produced, but with few particles. And now you need to push the particles to many particles, and that's the challenge.
Right,
But
right,
they're not noon states. Like a noon state, I would say that is really not within the reach of what we could do in 5 years, or, not even close. But the other states are in reach, but it's a very challenging experiment. But I think Philippe Boyer is a very able experimentalist, and Chris Westbrook as well. He's been working on these things already, so I am hoping that they will be able to jump the hurdles with the funding that we raised to be able to uh, reach the large masses that you need to test the new model.
okay. So I think let's
Thank you very much.
thank you
Thank you very much, and thanks again for your attention and for the possibility of being part of this beautiful celebration.
thank you very much. We hope to see you.
Thank you.
Thank you. Thank you very much.